consider an infinite plane sheet of charge carrying a uniformly distributed positive charge. Its surface charge density, sigma, is the charge per unit area of the sheet. That is, sigma is equal to Q by A, where Q is the charge on the sheet distributed over an area A. We can represent it as Q in is equal to sigma into A. Let the sheet be aligned parallel to the YZ plane such that the normal to this plane sheet of charge is along the x-axis. The electric field due to the positive charge will be directed away from the positive charge. In order to calculate the electric field strength, at a point P near the sheet of charge, let us now consider a Gaussian cylinder, one of the plane faces of which passes through P, and as such, the plane face is parallel to the plane of the sheet of charge. The point P is at a distance x from the sheet of charge. The point P lies on the circular surface of the Gaussian cylinder. We see that the cylinder extends to the other side of the sheet of charge, and the plane faces of the cylinder are equidistant from the plane sheet of charge. Let the plane circular faces of the cylinder be marked as 1 and 2, and the curved surface of the cylinder be 3. The total electric flux, phi, through the Gaussian cylinder is the sum of the electric flux, phi 1, phi 2, and phi 3 through the surfaces 1, 2, and 3 respectively of the Gaussian cylinder. Let this be equation 1. Let us first calculate the electric flux phi 1 through surface 1. According to Gauss law, we can write phi 1 equal to integral d phi 1. Here, d phi 1 is the electric flux through a small element of area dA on surface 1. d phi 1 is equal to E dot dA, where E is the electric field strength at the local element considered, and dA is the area vector with respect to the local element considered. Since E and dA are parallel to each other, E dot dA is equal to EdA cos 0, which is equal to EdA. Let this be equation 2. It is important to note that E is constant in magnitude for all points on S1. Now, phi 1 is equal to integral EdA. Since E is a constant, it is taken out of the integral. Then, phi 1 is equal to E into integral dA. Integral dA is equal to A, where A is the area of S1. Therefore, we get phi 1 is equal to EA. Since surface 2 is equivalent in all aspects to surface 1, the electric flux through surface 2, phi 2, is also equal to EA. Now consider surface 3, which is the curved surface of the Gaussian cylinder. At every point on the Gaussian cylinder, the electric field strength E and the outward normal to the surface, which represents the area vector, are perpendicular to each other. As the angle between the area vector and the direction of the electric field is 90 degrees, and as cos 90 degrees is 0, we have the flux phi 3 is equal to EdA cos 90, which is equal to 0. Hence, no flux passes through this surface. Thus, the flux phi 3 through this surface is 0. Substituting the values of phi 1, phi 2, phi 3 in the expression for total flux phi we get phi equal to 2EA. Let this be equation 3. According to Gauss law, phi is equal to Q in by epsilon naught. Substituting the value of Q in, we get phi is equal to sigma A by epsilon naught. Let this be equation 4. From the equations 3 and 4, we get 2EA equal to sigma A by epsilon naught. Simplifying this expression, we get E equal to sigma by 2 epsilon naught. Let this be equation 5. The expression for the electric field due to the infinite plane sheet of charge shows that the electric field strength due to it is independent of x. Vectorially, E is equal to sigma by 2 epsilon naught into n cap, where n cap is the unit vector perpendicular to the plane and passing away from it. If sigma is negative, then n cap will point towards the sheet of charge, and if sigma is positive, then n cap will point away from the sheet of charge. Thus, for an infinite large planar sheet of charge, the expression for E as given by equation 5 is approximately true in the middle regions of the planar sheet, away from the ends.